Okay, so in this video we're going to go through the Igneous rocks PowerPoint. And so instead of just jumping into IDing rocks, I just wanted to make sure we're all on the same page about where the heck they come from. So how do we get magma, which ultimately is going to give us igneous rocks? Because the definition, of course, of an igneous rock is that it's created from molten rock. And we talked about this a little bit when we talked about plate tectonics, but I wanted to kind of review and make sure everybody was up to speed on that. So what we're going to be doing in the next couple modules, so this one we're going to focus on, we just did minerals, then we'll do igneous rocks like you see here. So there are in this rock cycle a couple different versions of igneous rocks. There's ones that make it to the surface and erupt, and then cool and crystallize. And there's ones that never make it to the surface. They are molten in the subsurface, and they cool and crystallize in the subsurface. So we're going to talk about those today, but then in the next module we'll talk about how we get the other two classifications of rocks, our sedimentary rocks and our metamorphic rocks. Okay, so now, you've done this before because we did the Earth's interior already, so you have some knowledge of what the interior of the Earth looks like. It's got a core, an inner and outer, it's got a mantle, it's got a rigid part we call the lithosphere, it's got crust. So we're up to speed on all that stuff. And you know a little bit about plate tectonics. So we'll talk about how this brittle part of the Earth is in motion, and that there's pieces of this brittle part that are basically coming into contact with each other. And so they can collide into each other and converge, they can slide past, or they can be pulled away from each other. So you also have this in your knowledge bank. So let's put it together and figure out about igneous rocks. So the idea is that the process of moving these plates around, what's causing these plates to move, is kind of the process that's giving us magma, molten material, which eventually will cool and crystallize and give us our igneous rocks. So magma is molten rock that's inside the Earth. We use the term lava when we talk about molten rock on the surface. And so we know that as we go down into the Earth, it gets extremely hot. You've figured out some temperatures for this part of the planet. So why isn't there magma everywhere? Why is the Earth just not molten, gooey all the way through and through? So we know that pressure is kind of keeping most of the planet from being a solid, but how does it really look? And so what we end up seeing in my cool little drawing here from a cross-section of the Earth is that we don't have molten rock everywhere. What we do is have these little pockets of magma inside the Earth, and they're kind of near the surface here, and they're kind of distributed around, so I'll just put a little few dots there. We want to figure out why. What's causing melting to occur here? And so there's a few processes that are happening that allows the material inside the Earth to melt, become magma, and then ultimately cool and crystallize and become our igneous rocks. So how does that really work? Well, we got to think about how do we get rocks to melt? Well, if we have a rock at some depth inside the Earth, if we could change the heat right there, increase it dramatically, we could potentially cause it to melt. There are two other ways we can cause rocks to melt. The other is by decreasing the pressure. Because we know from our interior of the Earth that as we go down into the Earth, temperature rises, but pressure also increases. And they're having these adverse effects. Heat wants to melt the material, the rock. Pressure wants to keep it a solid. And so there's always that battle as we go deep in the Earth. And mostly pressure is winning. So if we can get rid of the pressure at some location, lower it, we could potentially allow it to melt. And the other thing we could do is change the composition of the material. What we see here is a lot of times if we add some molecular water at depth or some fluids, they can change some of the properties of the minerals. So remember, mineral properties are dictated by its composition. So if I can change its composition slightly, I can change some of its properties, and one of those could be the point at which it becomes molten. So when we look inside the Earth, we see that these are the three ways we're going to do it. We're either going to add heat at some localized part of inside the Earth and cause it to melt. We're going to add something to our rock, or we're going to move it. We're going to reduce the pressure. If we can do any or all of these things, we can cause some things to melt inside the Earth. And so what's driving all of this? Well, really, it's convection. The idea that part of the Earth is actually in motion. So as we go deep in the Earth, we know there's the asthenosphere. The lower and upper mantle actually behave like a fluid, even though they're a solid, right? So they have the ability to flow over long periods of time. So think about like silly putty or clay or something like that, where it's a solid, but if you kind of pulled on it really slowly, you can get it to move and flow without breaking. And so there's parts of the Earth that have this ability. And this is how heat is lost from the interior of the Earth, is when we heat something up, like the example here on the left, what we get is a hotter part of the water here. This is the cooler part. And when we change the temperature of the water or of substances, we change their densities. And so the water near the flame is less dense. The water at the top is more dense. So this stuff rises, pushes this more dense material out of the way, which sinks. We end up with these little currents that kind of circulate like this, where when you're near the heat source, you're hotter, you're less dense, you become buoyant, you rise. You're away from the heat source, you cool, and you become more dense and you sink. And so think that this is what's happening inside the Earth in some way, shape, or form. And so I'm going to show you a very, very simplified version of that, which would be something like this. Now, this is just to give you an idea of kind of how we can cause this melting to occur. But here's the core, our heat source. When the mantle is close to the core, it's being heated up. Its temperature increases. It becomes less dense. It starts to rise. As it rises up to the surface, it cools, and then it wants to sink, and then it sinks back down. And so what we see is at these places where it's rising and moving away, we get divergent plate boundaries here, where the crust or the lithosphere is being pulled apart here from the motion of this convecting mantle. And so why do we get molten material right here? It's because we're changing the pressure fairly rapidly. So although temperature is dropping, pressure is dropping a lot faster. And so in the case when it gets right here near the surface, temperature is winning the battle, and it starts to partially melt the mantle, and we can get some magma there. And so this is what we call decompression melting. It's a change in pressure. And that was one of the ways we said we could reduce or cause melting to occur. So here's a diagram of plate tectonics with some convection going on. So the idea is that the convecting mantle is coming up here, bringing material from deep inside the Earth. As it gets close to the surface here, the pressure is low enough, but the temperature is still high enough that we start to partially melt the mantle, and those little melts kind of collect together to form a chamber or a place where we have a large amount of molten material. And then when the crust is pulled apart, that molten material can rise up through those cracks and fissures and make it to the surface and create new crust here, cool and crystallize, and voila, we have some igneous rock that's here at the surface. We can also get some molten material happening where we have subduction. There's a couple things happening here. The idea is that when we take this rock here and push it deep into the Earth like this, this is rock that has existed for millions of years. And of course, along the surface here, we've collected lots of mineral deposits. Those mineral deposits have lots of water in them. And when we subduct this down into the Earth, those minerals break down, the water is released, and interacts with the mantle here, causing a compositional change, which allows this to start to partially melt because we've made some slight changes to the composition of some of the minerals there. They have a lower melting temperature once they change, causes them to partially melt, Once again, we can collect those little melts into little pockets. We can get magma chambers, and voila, we get magma. And so, at divergent plate boundaries, we're going to argue that we have decompression melting, and that's because we have mantle rising up, pressure's dropping, we start to get a melt here. If this cools and crystallizes at depth, we would get what we call intrusive igneous rocks, rocks that cooled inside. If it made it to the surface, we would call them extrusive, molten material that made it to the outside of the Earth. Right? At convergent plate boundaries, we usually would argue that we have the compositional change from pulling the water off the minerals that are being subducted down into here. There's also a heat interaction here that could be occurring. So there's a couple things happening, but we can melt this material, starts to rise up, interacts with the crust. In some cases it does, it mixes and interacts. In other cases it kind of pools at the base of the crust here, or I guess this is the continental crust here in this diagram, and that pooling is a heat source for this material here, which then increases the heat here and can cause melting to occur right here. So we have two things kind of happening there. And then at our hot spots, even though we don't have plate tectonics, we still have this rising plume, which means it's decompression melting occurring. And so we're decompressing, so the pressure is dropping, temperature is still relatively high, and so right here near the crust here we get some melting and we can generate some magma there. Okay, so the take home for this initial thing is magma inside the Earth. It's being created because we're either increasing temperature, decreasing pressure, or changing the composition. Convection is playing a role in moving around heat inside the Earth, which is moving plates, which is causing decompression melting or some other change in composition melting. And this is the kind of processes that are occurring in here. And of course, transform boundaries aren't here because there's no process that would cause melting at a transform boundary because none of these are happening there. And this is why we wouldn't get magma there. Okay, so that might take a little longer than I wanted, so we'll try and keep moving here. So, when we look at igneous rocks, we basically want to determine if they made it to the surface or if they cooled inside. And we can do that relatively easily by looking at the crystal size. So we're going to use the term intrusive to describe rocks that cooled inside the Earth, or plutonic rocks. So plutonic and intrusive can both be used to describe these. Or extrusive to describe rocks that made it to the surface and cooled, or volcanic. So those can use interchangeably. The argument here is that larger crystals would grow inside the Earth because the crystals formed slower, so they cooled a little slower, and so they had time to grow in size, whereas when they made it to the surface, the difference in the air temperature and the molten rock is extreme, and so they cool within days, whereas the ones inside the Earth can take thousands and thousands of years to cool and crystallize. So the slower cooling rate allows larger crystals to form. And so we're going to use that first thing, this idea of crystal size, to help us identify igneous rocks. And we're going to call that texture. So the texture is either coarsely crystalline or finely crystalline, and it tells us something about where the igneous rock cooled and crystallized. Inside the Earth, big crystals. On the surface, small crystals. We can also use, in general, the color of the igneous rocks to tell us something. And that color is going to tell us composition in general. What we're going to argue is the darker minerals that make up these rocks up here have a different composition because they contain lots of dark minerals than the composition of the material down here that contain lots of lighter minerals. And so the color is going to be an indication of its composition. So we can use composition and texture to then name some of these igneous rocks. So you'll need to be able to identify relative color and some different textures to be able to give names to these igneous rocks. Okay? So when we look at crystal size, it's telling us something about how it cools. Bigger the crystals in general, we would say slower cooling. And so the one on the left, very slow, probably cooled inside the earth. The one in the middle, small, cooled on the surface. No crystals, holy crap, cooled super fast. Okay? And then light versus dark. So we want to look at minerals and kind of put them in an order or a grouping of the light ones versus the dark ones. So when they're smaller crystals, like the pictures here, sometimes it's a lot easier. We can just say, hey, that's a very black mineral, that's dark. That's a very black rock, and then a very white rock. So those are on the extremes there of compositions. Then the gray one would fall in the middle. When they're large crystals, we just want to look at the amount of dark minerals that we can visually see with our eye. If you have a whole bunch of them, they go in the dark pile. Not many, they go in the light pile. And this is also telling us kind of what was melted to create these. As a general rule, we get the mantle, that is what's partially melting through the processes we just described, or we could melt the crust. And so when we talked about the interior of the earth, we did mention that the mantle is made of mostly very dark colored minerals, high in iron and magnesium, whereas the continental crust is made of very light minerals, a lot of silicates or a lot of aluminum, potassiums, calciums, sodiums, things like that. So we're going to apply some terms to that that'll help us name some of these things. So the term we're going to apply to the dark colored rocks, igneous rocks, is mafic. And so the term mafic is meaning that these magmas are rich in iron and magnesium, but they don't have a lot of silica or sodium or potassium. But the big ones are the iron and magnesium are really making the dark colored minerals, which are giving the rock a dark appearance. And so mafic rocks are very dark in color. Here's that Bowen's reaction series, just slightly different version of it. But what we're arguing for a rock that we're going to call mafic is that it contains a lot of these minerals that are high in iron and magnesium. This is why it's dark in color. It tells us something about where it originated. Okay? And so when we look at what are called mafic rocks, we would argue that the term basalt and gabbro describe a rock that has the same composition. The difference being where it cooled and crystallized. Gabbro has large crystals, means it cooled inside the earth. Basalt has small crystals, means it made it to the surface. But because they're both dark in color, they're both high in iron and magnesium, we would call these rocks mafic based on their color. Okay? The peridotite that you see here is something we would call ultramafic because it is super high in iron and magnesium. Mafic is the composition that we associate with the oceanic crust that is composed of rocks like this. The mantle is something that we call ultramafic. It is composed of rocks that look something like this. Okay, but this is a compositional term, both of these, and it really has to do with the amount of elements and minerals that make up these rocks. And for us, we're just using color to help us do that. Because if I know it's dark in color, then I know potentially where it might have come from the oceanic crust. Okay? And we argued that how did it originally form? We talked about this. We partially melted the mantle. We don't melt every mineral in the mantle. We only melt the ones with the lowest melting temperature. And that ends up forming a mafic magma, which is gabbro or basalt. The mafic magma that cools at depth gives me gabbro. The mafic magma that makes it to the surface gives me basalt. Okay? And then, of course, we have the intermediate magmas. So we have mafic on one end, high in iron and magnesium. On the other extreme, we have what are called felsic rocks. Those are super light. Well, then, of course, we have something that kind of falls in the middle, and we give that term intermediate to those magmas. And so same thing. So they have less dark minerals than mafic, but more than the felsic. And so they fall kind of in the middle of my Bowen's reaction series. These are the minerals that I would expect to find in an intermediate magma. And so when we look at those, these are the rock names associated with those. So an andesite and a diorite. So although this andesite, it might not be the best image, although you can see larger crystals here, there's also a portion that are very small, and that's the kind of darker background that's here. And so our rule usually is that if you look at a sample and all of the crystals are large, you can easily see all of them with your naked eye, that's going to be coarsely crystalline. We're going to argue that that's an intrusive igneous rock, which diorite is. The andesite has some dark, or some small, and some big, right? So if we can't see them all easily with our naked eye, we're still going to classify this as being finely crystalline. So this would have cooled at or near the surface. And how do we get intermediate rocks? Well, it's a mix of the mafic magma and a felsic magma. And so we can get that at subduction zones. And so this is where we have molten material created in the mantle, which is mafic, and as it rises up, it interacts with a felsic continental crust, and it can make an intermediate version of my igneous rocks. And then we have the felsic magma. So these are the ones that are really poor in iron magnesium. They have a ton of silica. They have a ton of sodium and potassium. Okay, and so these have minerals that are in the bottom of my Bowen series. Lots of quartz and micas and feldspars. They're very light in color. And so they're either overall light if they're finely crystalline, or in the image here on the left, they have few dark minerals here compared to a mafic coarsely crystalline rock where all of the minerals would be coarse and dark in color. And so when we look at some samples here, this is the finely crystalline igneous rock. It is very light in color. So this is our rhyolite. The intrusive version of that is this granite, because the black minerals are not very abundant. It is low in these very dark minerals, meaning it's low in iron and magnesium. This is my granite. It cooled inside the earth because it has larger crystals. So these would come from melting of the continental crust, because this is my felsic source. When I melt the mantle, when I partially melt it, I get a mafic melt. And so in order to get different compositions, I have to interact with different things. So if I have a mafic melt and it interacts with a felsic rock and melts that, a mafic and a felsic mixed, let's say perfectly 50-50 together, that's an intermediate melt. And that would give me an intermediate igneous rock. In order to get a rhyolite or a granite, I need to melt the continental crust. So I have a mafic melt that kind of sits at the base of my crust here and acts as a heat source and causes the continental crust to melt. There's not much interaction between mafic and felsic. And so I have very light colored igneous rocks because I didn't mix very well. I melted the continental crust, which is felsic, and then when it recrystallizes, it's felsic. Okay, so this is an explanation for how we would get felsic igneous rocks. And so we talked about this kind of pooling here, right, at the base that melts the continental crust here. And now pumice, because it's light in color, we would still call it felsic, just has a unique texture. You can't see any big crystals, so that would mean it was small crystals, mean it made it to the surface. But the holes, the abundant holes that you see here, is an indication that there's lots of gas trapped in the magma, and that can be something useful for us when we try to interpret what's going on here, right? Okay, so here's what we got going on. You should be aware that crystal size is an indication of where the magma cooled, and we would argue big crystals, slow cooling inside the Earth, small crystals, fast cooling on the surface of the Earth. Composition is dictated by its color, and we would argue that these two have the same composition. Maybe not like identical, but in our terms we're having these three big kind of groups, Felsic, intermediate, and Mafic. These are both Felsic in composition. Big crystals, coarse texture, right? Slow cooling at depth. Small crystals, doesn't matter what composition, it's still considered extrusive, cooled on the surface if it's got small crystals, okay, because it cooled relatively quickly, okay. Obsidian is a unique type of igneous rock. There's no crystals that can be seen. The argument here is that it cooled extremely quickly, so potentially it flowed into some water, or there's a process that caused it to quench very quickly, and so crystals didn't have time to form, and so we get this unique kind of glassy texture. Another texture we mentioned before is the holes. It's called vesicular texture. Here I have a dark colored rock with holes in it, not like the pumice we just looked at that was light with holes. So they're different rocks because of that. This is dark in color. It's mafic, but it has holes. The holes still mean the same thing. There was gas trapped in the magma. But they're different rocks because they have different compositions. Okay? And then another texture we could talk about, it's a little harder to kind of see or visualize, is something called a pyroclastic texture. This is where we have fragments from a volcanic eruption that actually get ejected from a volcano. When they land, they're hot enough that they weld together and they form a rock. So sometimes if the pieces are very, very tiny that kind of all weld together, we might call that a tuff. Or if they're larger pieces, we can get some other names for that. But when we look at that texture, we would be able to tell something about interpreting what's happening here, that was from an explosive eruption. And so look, how the game is played when we're trying to figure out what type of rocks we have and we want to name them, is we would use a chart like this. And so if you're given a handful of samples, your mission is to determine their composition. And so the unique ultramafic rocks that we rarely see at the surface was a picture of that rock that had the very large crystalline olivine, the very green mineral. And so when we see something like that, we would argue that it's what's called a peridotite, and it's interpreted to be a sample of the mantle. Okay? But we don't see those very commonly. And look, for us, we really just talked about coarse-grained or coarsely crystalline igneous rocks, finely crystalline igneous rocks, vesicular, glassy, and pyroclastic. We really didn't talk about this term here, so we can kind of gray that out for now, not think about it. But the idea is that if you were given a sample, you would have to determine, is it very dark, very light, or somewhere in the middle? And look, sometimes you need all three samples together to know where the intermediate. If you have a black rock, a gray rock, and a white rock, you should be able to tell me which is which. If I just threw a gray rock at you, you might be like, I don't know, is it dark enough to be mafic, or is it light enough to be felsic? But in comparison to other rocks, you should be able to determine its general composition. And you should be able to determine whether all of the crystals that you can see with your naked eye are big, or there's small crystals that you can't see. And basically you're going to use those two identifiers to name it. If it's very light, has very small amount of dark minerals, and you can see them all with your naked eye, it's a granite. But if you can see all of the crystals with your naked eye, but they're all black, it's a gabbro. And if it's about 50-50, it's called a diorite. If we have a very dark finely crystalline igneous rock. Dark means mafic. Finely crystalline must be a basalt. Light colored, can't see all the crystals, must be felsic. Can't see the crystals, must be fine, must be a rhyolite. So this is how we would name the rocks, right? So the pumice has holes, but is lighter in color. Scoria is dark, has holes, right? So the color is giving us a different name. For our glassy texture, we're just calling it volcanic glass. So there's always some weirdness going on here. But the main rocks that we talk about in class are going to be rhyolite, andesite, basalts. Why for this class? Because mostly these are volcanic rocks. This is a hazard. This is what's going to talk to us or tell us about the type of volcanism we're going to get and the type of hazards we're going to get. So we want to be able to identify those samples for sure. But for this lecture material, you should know some of the terms, of course: felsic, intermediate mafic, what they mean, where they come from, how rocks melt, and then what do the textures tell us about cooling rate or some other unusual kind of information. Lots of gas for vesicular, explosive for pyroclastic, and things like that, right? So these are kind of the terms you want to do. And then the lab will look at some samples. We'll look at some imagery and try to use your knowledge of color and texture to name some igneous rocks. And so next time when we do more rocks, we'll do some sedimentary rocks and some metamorphic rocks, and a few little additional information if you so choose to look those things up. All right, I know that was a little long. Sorry about that. So questions, comments, feel free to contact me if you still have some questions.